Welcome to our second part of the lecture series. Today we will talk about the climatic effects on water isotopes. Let's first start with a closed system. The typical 18 to 16:0 ratio between water and vapor is at room temperature about 9 per mil, 0.9%. If we increase the temperature, the ratio drops because it is relatively speaking easier to kick out the heavier molecules from the water into the vapor. When we open the system, which means we allow the air to be unsaturated with water vapor, which means a relative humidity below 100%, like in the real atmosphere, more lighter water vapor will escape, which means we have a depletion in heavier 18O. The water vapor attains delta 18O values of -10 per mil. Understanding this, we can now go to the global water cycle, or people also call it the hydrological cycle. Ocean water with 0 per mil delta 18O standard water evaporates in an open system. The water vapor will be depleted by 10 per mil. Clouds form and the first rain falls, with raindrops enriched in delta 18O relative to the vapor. Let's say rain falls with -3 per mil, then the remaining vapor attains a value of -13 per mil. More and heavier rain falls as the vapor is moved to colder regions. If the rain falls with a delta 18O of -10, the remaining vapor will be heavily depleted, -20 per mil, and so on and so forth. If the rain with -10 per mil falls, for instance, into a water reservoir, lake, part of it will be evaporated, and we obtain a slight enrichment again, -9 per mil. This is a typical value of tap water or the water coming out of your shower in the morning. By knowing something about this secret number, you can learn something about the global water cycle. We can formalize the ideas on the last slide a little bit more. We have learned that water vapor becomes more and more depleted in heavy delta 18O as vapor moves to higher latitudes and loses heavier water molecules through rainout along their path. Of course, also the moisture content decreases in response to cooling, because colder air cannot hold as much moisture. The initial water vapor on its path from warm oceans to cold ice, from equator to poles in the atmosphere, starts with a delta 18O value of roughly -10 per mil and an initial vapor fraction of, call it F equals 1. As the remaining vapor fraction, F, decreases under cooling and transport in the atmosphere, the ratio R of water vapor decreases too. And this is expressed by the so-called Rayleigh distillation model. R equals Ri divided by the remaining fraction to the power of 0.0092. The colder it is on our planet, the drier it will be, and the lower, more negative, the 18 to 16 ratio of both water vapor and rainfall will be. This is a prediction of the theory. Willy Dunsgaard, a Danish scientist, in 1964 measured the delta 18O of rainfall in many different places in the world and plotted the values against the annual mean temperature. He found an excellent linear relationship confirming the original theory of Rayleigh distillation. What about Korea? Korea's rainfall has about -7 per mil rainfall delta 18O. According to the Dunsgaard relationship, the annual mean temperature in Korea should be around 11 to 12 Celsius. This is actually not a bad estimate. The annual mean temperature in Seoul is about 13 degrees Celsius. So, by measuring rainfall delta 18O and knowing the Rayleigh distillation law, we can calculate the annual mean temperature. Raindrops tell us something about temperature and climate. Pretty cool, right? If delta 18O is such a powerful tool to learn something about climate and the hydrological cycle, what about the delta 18O value of seawater? Before, we have always assumed it is close to zero. This is true in a global mean sense, but ocean measurements show that there are areas with positive delta 18O and areas with negative values. How can this be? It also looks like the lower values are mostly found in the extratropics and polar regions. In the subtropics, it is dry and water evaporates, which leaves behind a 18O enriched surface water, such as in the North Atlantic. Then, as we learned already, the water vapor moves poleward, cooling down, and any rainfall occurring and falling into the ocean will be more and more depleted in 18O, creating negative values of delta 18O along their path. Therefore, this image tells us something about the water transportation pathways. Lots of evaporation, high delta 18O in subtropics, and lots of precipitation, negative delta 18O in extratropics, such as the North Pacific. It also turns out that the global ocean salinity, concentration of sea salt, mostly NaCl, has a very similar pattern. We leave it up to you to discuss why. There is another fascinating relationship between delta 18O of rainfall and climate. If we study the relationship between delta 18O and regional rainfall at many places around the world, we also see a negative relationship. The more rainfall there is, let's say in a massive downpour, the more depleted the water will be in heavy delta 18O. How does this work? It seems to be a bit counterintuitive to our previous finding, which suggested that as the atmosphere gets drier, delta 18O of rainfall also decreases. In fact, this relationship, which we call the amount effect, is not that easy to explain, and it's also not a universal relationship worldwide. There are many places on our planet where it does not hold. However, in the tropical regions and in main global monsoon regions, the relationship is quite robust. There are three main mechanisms that can cause this relationship. Number one, a light rain in a relatively dry air is associated with evaporation of lighter 16O in the raindrops and a relative enrichment of delta 18O of rain reaching the surface. In heavier rain, the humidity is higher and less light 16O can evaporate, creating a more depleted negative signal in delta 18O. Number two, the initial rain in a rain event is enriched in delta 18O relative to the water vapor according to equilibrium fractionation. If rainfall continues, much of the heavier 18O has already rained out and the remaining raining water will then be relatively depleted. Number 3, a third candidate to explain this interesting relationship has something to do with where the water vapor actually came from. Therefore, measurements of delta 18O of rainfall in Kewin will tell us something about the precipitation amount, the cloud-specific rainfall processes, and the source of the original water vapor. There is a large number of stations in the world that continuously monitor delta 18O of rainfall. They're called GNIP stations, Global Network of Isotopes in Precipitation. So far, there is only one active station in Korea, the one from our center. The Kewin project will provide additional spatial information on how water isotopes change seasonally and from year to year. Well, water is a key element of the climate system. This opens the possibility that we can use water isotopes in a variety of forms, such as from samples taken from rivers, lakes, and water reservoirs, water dripping from the ceiling of a cave, in ice cores or in the ocean, and of course precipitation, to learn something about the processes governing the climate on our planet. Let's start with the coldest places on our planet, the big ice caps of Greenland and Antarctica. Some of my colleagues drill kilometer-long cores of ice that go back about 100,000 years for Greenland and almost 1 million years for Antarctica. Ice is frozen water, so we can easily measure delta 18O. This is usually done with little laser spectrometers similar to the one that our center will be using for the Kewin water samples. What scientists found in delta 18O in Greenland was absolutely astonishing and took everyone by surprise. Looking at the time period from 10 to 60,000 years ago, which covers part of the last ice age, you remember when sea level was 120 meters lower than now, the delta 18O shows some abrupt jumps. Interpreting these jumps in terms of temperature, remember the Dunskat relationship, scientists concluded that the climate system was able to jump rapidly within 10 to 40 years between a cold and a warm state. Over Greenland, these variations are large, up to 10 degrees Celsius. Later on, scientists concluded, using other paleoclimate data sets from around the world, that this phenomenon, known as Dunskat-Oeschger events, existed worldwide. However, interestingly, in the southern hemisphere, we see an antiphase response. Greenland warm, Antarctica cold, Greenland cold, Antarctica warm. It is still not 100% clear what caused this variability, but our center in Busan is intensely studying these type of abrupt events. We think that rapid changes in the glacial ice sheets over Europe and North America triggered changes in the Atlantic circulation, which then impacted global climate. Another fascinating way to use oxygen isotopes in reconstructing climate of the past are ocean sediment cores. Scientists go out in big ships, such as the JOIDES Resolution shown here, to extract mud cores from the deep ocean. What looks like mud has allowed scientists to learn a lot about the climate system. If we look closer under a microscope, we find little plankton fossils, some of which lived at the ocean surface and others lived at the ocean bottom. They are made out of calcium carbonate, which is CaCO3. There are 3 oxygen molecules embedded in the calcium carbonate, and there is hence the possibility that either 18O or 16O from the surrounding ocean waters can sneak into the process of calcium carbonate formation. We already learned that under glacial conditions, the delta 18O of seawater was about 1 per mil higher than presently. Sea level was 120 meters lower. How do we know this? We know this from analyzing the delta 18O of calcium carbonate of these little microfossils. These measurements are a bit more complicated than for ice. They have to be done with an isotope ratio mass spectrometer. With such data, climate scientists then can learn something about sea level, number one, number two, past temperatures, number three, past rainfall variations, using mud cores from the deep ocean. Even though I have worked with such data for the last 15 years, I still find this story astonishing. From ice caps to the deep ocean, what other cool places do climate scientists visit? My all-time favorite are caves. Here we take a look at a cross-section through the soil and rocks in an area that has limestone caves, such as in Gangwon district, in northeastern part of South Korea. Limestone is essentially calcium carbonate, CaCO3. First, we have a soil layer with vegetation, microbes, clay and other materials. Water from the rain can percolate through this layer slowly, absorbing CO2 and becoming carbonic acid until it eventually reaches the limestone epikarst layer. There it slowly seeps through little cracks and slowly dissolves the limestone CaCO3 to form calcium bicarbonate, also called calcium hydrogen carbon, in aqueous solution. As it drips into the cave, we have the reverse reaction. CO2 can outgas and calcium carbonate is formed. This is the mechanism that creates amazing stalagmites and stalactites, also known as speleothems. Now, what does this all have to do with oxygen and water isotopes? Rain with a specific delta 18O value, let's say -8 per mil, falls onto the surface. Evaporation, which is related to winds, temperature, atmospheric humidity and land vegetation, makes it slightly heavier, -7 per mil. As the water enters the soil and the epikarst, it may also change its delta 18O value slightly due to the dissolution of the surrounding limestone, which can have a typical delta 18O value of -3 per mil. Then it drips into the cave, an environment with almost 100% relative humidity, which means that equilibrium, temperature-dependent fractionation will take place between delta 18O of the water and the water vapor. The fractionation between delta 18O of cave water and calcium carbonate is then again an equilibrium process with temperature-dependent fractionation. If we know the delta 18O of the calcite and that of the water, we can then calculate from the equation in this slide the temperature that existed inside the cave during the process of calcification. Clearly, the difference between rainfall delta 18O and stalagmite delta 18O of calcium carbonate is controlled by a variety of processes, including temperature inside the cave. Nevertheless, even though it sounds complicated, speleothem delta 18O records have become a very powerful tool of reconstructing past climates. I will show some more examples later.